Okay, in this video we're going to be looking at the sampling distributions and estimators. We'll be looking at sampling distributions of a sample mean, a sample variance, and a sample proportion. And then we'll talk about estimators, both biased and unbiased estimators. Okay, so here's what a definition of a sampling mean is. The sampling distribution of a statistic, and that statistic can be something like a sample mean or a sample proportion or a even a sample variance. Okay, so the sampling distribution of a statistic is the distribution of all values of the statistic when all possible samples of the same size okay. And that same size is going to be n are taken from the sample population. Or it should be taken from the same population. Okay. 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 So the sampling distribution, by definition, is just simply the distribution of all the values of that statistic, whether it's a mean, a variance, or a proportion, when all possible samples of the same size, n, are taken from the same population. Okay. And an illustration of that would be this. Let's say I had a population, which is going to be this figure here. Let's say I had numbers like 6, 8, 12, 9, 5, 4, 3, 7, and 11. Okay. And I want to take samples of the same size. So here I'm taking a sample of size 3, another sample of size 3, and these remaining numbers will be a third sample of size 3. So in this case here, let's say I wanted to take the mean of each of these individual samples here. So here, sample 1 has this, 6, 8, and 9. And if I take the mean, I just simply add those numbers together and divide by 3. So in this case here, 6 plus 8 plus 9, and that's 23 divided by 3, would be approximately 7.7. And then I got this sample right here, which is 12, 5, and 4, and I want its mean. Well, that's 17 plus 4, that's 21 divided by 3. and that will give you 7. And then the third one, 3, 7, and 11, that's going to be 18 plus 3, that's 21. Okay, add 3, 7, and 11, that's 21. 21 divided by 3 is also 7. Okay, so if I take, let's say, the mean of these, the average of these means, okay, so here this case, that was, that first one was 1423 divided by 7, and then plus 7, I'm sorry, 23 divided by 3, and then plus 7, divide that by 3. The average of all these means, sometimes it's called sigma of x. No, take that back, that's mu of x bar. The mean of all of your means, in this case, that's approximately 7.2. And then, if I add these 9 numbers together, as is, add 6 and 8 and 9, 12, 5 and 4, 3, 7, and 11, that total is 65. 65 divided by 9 would be 7.2 approximately. So as you can see here, the mean of all of these is the same as the mean of your sample means. Okay, so that's basically what that sampling distribution is. Okay, now the same holds true, and I'll go ahead and put this up here. And we just got through talking about the definition of a sampling distribution of a sample mean. That's the distribution of all possible means, or the distribution of the variable x bar with all samples having the same size n taken from the same population. Okay? And we can also use that same population for a sampling distribution of a variance. Okay, so here the sampling distribution of the variance is the distribution of the sample variance with all samples having the same sample size n taken from the same population. Okay, and additionally, this is also for a sample proportion. That's the sampling distribution of the sample proportion. It's the distribution of the sample proportions with all samples having the same size n taken from the same population. Okay. So here we can use that sampling distribution to do some of these particular problems here, which we'll get to in a few minutes. Now, there's also one more thing I need to talk about, and that's the estimators. One is biased and the other one is unbiased. So in this case here, let's talk about estimators. Now let's define what an estimator is. It is a statistic used to infer or to estimate the value of a population parameter. Okay. All right. An estimator is a statistic used to infer or to estimate the value of a population parameter. And also, more specifically, we have an unbiased estimator. And definition for that is going to be a statistic that targets the value of the population parameter. In the sense that the sampling distribution of the statistic has a mean that is equal to the mean of the corresponding parameter. Okay. So that's what the definition of an unbiased estimator is. Okay, it's a statistic that will target the value of the population parameter where that the sampling distribution of that statistic has a mean that is equal to the mean of the corresponding parameter. And there are three unbiased estimators. One of them is the mean, which is in this case your X bar. And in fact, I did do a illustration of a situation where I had all of this as a population. I took a sample size of 3 each, and you can see here that the mean of each of the individual means is the same as the mean of the whole entire population. So here, this will be considered as an unbiased estimator. The mean is your unbiased estimator. Next is a variance, which is usually S squared. The third is a proportion. Now, proportion, its notation is going to be p hat. Okay. Now, the opposite of unbiased estimators would be biased estimators. Okay. So here, biased estimators are statistics that do not target the value of the corresponding population parameter. And there are three biased estimators. One of them is the median. In this case, the median does not target the value of the population parameter. The next one is the range. And the third one is standard deviation. Which is, of course, lowercase s. But with the standard deviation, that bias is very small. Okay. Okay. The bias with the standard deviation is very small, so pretty much lowercase s is often used to estimate sigma, even though it is a biased estimator. Okay. So those are your biased estimators and your unbiased estimators. Now let's look at some examples of just this. Okay, let's start with this first example. All right, in this case, three randomly selected households are surveyed. The number of people in the household are 2, 3, and 10. Assume that samples of size n is equal to 2 are randomly selected with replacement from the population of 2, 3, and 10. Listed below are the 9 different samples. Complete parts A through C. In part A, you to find the median of each of the 9 samples. Then summarize the sampling distribution of the medians in the format of a table representing the probability distribution of the distinct median values. Okay? So let's start off with part A. And in this case here, I'm going to have my sample and then the median. So I have 2, 2, 2, 3, 2, 10, 3, 2, 3, 3, 3, 10, 10, 2, 10, 3, and 10, 10. Okay, now to find the median of a set of data, you always, here we got two numbers, so we have to take the average of the two numbers here to get the median. So here if we add 2 plus 2, you can get 4. 4 divided by 2 will be 2. For 2 and 3, 2 plus 3 will be 5. 5 divided by 2 will be 2.5. For 2 and 10, 2 plus 10 is 12. 12 divided by 2 will be 6. And then 3 and 2 will be 5 divided by 2 will be 2.5. For 3 and 3, that will be 6. 6 divided by 2 will be 3. And then for 3 and 10, that's 13 divided by 2. That's 6.5. 10 and 2 is 12. 12 divided by 2 will be 6. 10 and 3 will be 13 divided by 2 will be 6.5. And then 10 and 10, that's 20. 20 divided by 2 will be 10. Okay, now I'm going to take that and condense that as a probability distribution. So on the right, I'll put sample median. And then the probability. Alright, so the sample medians that we have here are just 2. I also see 2.5. I also see 3. I also see 6, 6.5, and 10. Okay? Now for the sample median of 2, there's only one sample median of 2 here out of 9. So this will be 1 over 9. So the probability of a sample median of 2 will be 1/9. For 2.5, there are 1, 2 out of 9. So that probability will be 2/9. For 3, there's only 1 median of 3, so that's 1/9. For 6, there are 2. So the probability of getting a sample median of 6 will be 2/9. 6.5, there are also 2, so that's going to be 2/9. And for 10, there's only 1. So it'll be 1/9. Okay, so that's how we do our probability distribution here. Okay, because I have 9 medians here. And these are the only medians that I have here that's given to me in that problem. Okay, so that's going to be your sampling distribution of medians in the format of a table representing the probability distribution. So that's part A. Now, part B says this. Find the median of each of the 9 samples. Then compare the population median to the mean of the sample medians. Compare the population median to the mean of the sample medians. Okay. Now let's look at the numbers that we have here. 2, 3, and 10. Now those numbers are in numerical order. And there are three numbers that we have an odd set of data, so the median is going to be the middle number in this set for 2, 3, and 10. The middle number in this case is 3. So the median there is going to be 3. Okay, now they want to compare that to the mean of the sample medians. Okay, well, let's do this. We're going to take the sum of all of these medians here and divide by 9. So here, I'm going to call this X bar of your sample medians. And that's this. 2 plus 2.5 plus 6 plus 2.5 plus 3 plus 6.5 plus 6 plus 6.5 plus 10. And I might need to change that to mu. Because we're pretty much treating this as a population. Okay. So the sum of these, and that's 10, will be divided by 9. Now if I add all these up, this will give you 45. 45 divided by 9 will give me 5. So the mean of my sample medians is going to be 5, which is different from the median that I got of 3 for those 3 data values, 2, 3, and 10. So the next problem is this. I'm going to bring this down for part C. Do the sample medians target the value of the population median? In general, do the sample medians make good estimators of the population medians? Why or why not? Okay. And the reason for it, well, the answer is going to be no. Because the median of my 3 numbers, 2, 3, and 10, is not the same as the mean of the sample medians. So in this case, we can say that sample medians do not target the population median. Okay. And because of that, the sample medians do not make good estimations of the population medians. Okay. All right, and I will do another one. All right, let's say we had something like this. You have 3 randomly selected houses, and they are surveyed. the number of people in the households are 1, 3, and 8. Assume that samples of size n is equal to 2 are randomly selected with replacement from the population of 1, 3, and 8. Construct a probability distribution table that describes the sampling distribution of the proportion of odd numbers when samples of sizes n is equal to 2 are randomly selected. Do the mean of the sample proportions equal the proportion of the odd numbers in the population? Do the sample proportions target the value of the population proportion? And does the sample proportion make a good estimator of the population proportion? And listed below are 9 possible samples. Okay, so in this case here, I'm going to list all my samples. And the proportion, now we're dealing with the proportion of odd numbers of size n is equal to 2. So we got 1, 1, 1, 3, 1, 8, 3, 1, 3, 3, 3, 8, 8, 1, 8, 3, 8, 8. And here we're going to list our proportions in the form of a fraction, well, as a decimal. Okay. For 1 and 1, they're both odd. So the proportion of odd numbers in that sample of 2 would be 1. Now that's what 2 out of 2, which is going to be 1. 1 and 3 are both odd. So that's 2 over 2, which is also 1. 1 and 8. Out of the 2, there's only one odd number. So 1 divided by 2, that will be 0.5. Okay. 3 and 1 are both odd, so that's 2 out of 2, which will be 1. 3 and 3, they're both odd, so that's 2 over 2, which is also 1. 8 and 1, well, 3 and 8, I'm sorry, 3 and 8. Only one number is odd, that's your 3, so that's 1 out of 2, or 0.5. For 8, only 1 is odd, so 1 out of 2 will be 0.5. 8 and 3, there's only one odd number, that's your 3 here. 1 out of 2 will be 0.5. And then 8 and 8, none of these are odd, so that proportion will be 0. Okay, so the only numbers we have for our proportions are 0, 0.5, and 1. So on the right side, I'm going to write down sample proportion. And probability. Now in this case here, our sample proportions are either 0, 0.5, and 1. Now, if you look at this, how many zeros for our proportion do we have out of 9? Only 1 0. So that probability is 1/9. For 0.5, 4 of these samples have a proportion of 0.5 out of 9. So that's 4 out of 9. And then for 1, again, 4 of those samples have a proportion of 1, so it'll be, again, 4/9. Okay, so that's your probability distribution there. Okay, next is, does the mean of the sample proportions equal the proportion of odd numbers in the population? Okay. Let's get the mean of the sample proportions. That's going to be mu of your sample proportions. We just simply add these numbers up and divide by 9. So in this case here, we got 1 plus 1 plus 0.5 plus 1 plus 1 plus 0.5 plus 0.5 plus 0.5 plus 0. All of that is divided by 9. So in this case here, if we add those numbers up, you're going to get 6 over 9. And 6 over 9 would simply be 2/3. So the mean of the sample proportion would simply be 2/3. Okay. Now the numbers that we have in our population are 1, 3, and 8. Okay. Now, let's get the proportion of odd numbers. If you look at this, there are 2 odd numbers out of the total of 3. So we can write that as 2/3. So the proportion of odd numbers in that population would be 2/3. And in this case, we can see that the mean of the sample proportions do equal to the proportion of odd numbers in that population. Okay? And because of that, we see that the sample proportions target the population of odd numbers in the population. So we can say that the sample proportions target the proportion of odd numbers in the population. And that means that your sample proportions do make good estimators of the population proportion because of that fact. Okay. Okay, let's look at this next example. Okay, now this one we're dealing with a mean. All right, the assets in billions of dollars of the 4 wealthiest people in a particular country are 44, 34, 33, and 14. Assume that samples of size 2 are randomly selected with replacement. And it's going to be selected with replacement from this population of 4 values. After listing the possible samples and finding the mean of each sample, use a table to describe the sampling distribution of the sample means. So this will be part A, and then you're going to find the mean of the sampling distribution. Okay, so in this case here, what I want to do is just create a table. On the left side, I have my sample of size n is equal to 2, and the mean of each individual sample. Now my population are those numbers 44, 34, 33, and 14. Okay, that's my population here. Okay, now with replacement, that means that each one of those will have a chance of being selected. So my first sample will be 44 and 44. The second one will be 43 and 34. The second one will be, this will be 44 and 34. And then 44 and 33. And then 44 and 14. Okay, let me make that 44. Okay, and then for 34, I can have 34 and 44, 34 and itself, 34 and 33, and then 34 and 14. Okay, and then the next set, starting with 33, I have 33 and 44, 33 and 34, 33 and itself, 33 and 14. And then, if I start with 14, I compare 14 with 44, 14 and 34, 14 and 33, and finally 14 and itself. So if you look at this, I got like 16 different samples of size n is equal to 2. 16 different samples. So each one of these, I'm going to have to find the mean. Okay, and I just simply take the average of the two numbers here. So 44 plus 44, that's 88 divided by 2, which will be 44. 44 and 34, that's 78 divided by 2, that will be 39. 44 and 33 will be 77 divided by 2, that's 38.5. 44 and 14 will be 58 divided by 2, which will be 29. And then do 34 plus 44 is 78 divided by 2, which will be 39. And then 34 plus 34 is 68 divided by 2, which will be 34. 34 and 33 is 77. 77 divided by 2 will be 33.5. 34 plus 14 is 48. 48 divided by 2 is 24. 34 and 44 is 77 divided by 2, which will be 38.5. 33 and 34 is 68 divided by 2, which will be 33 and 34 is 67 divided by 2 is 38.5. I think I made a mistake here. This is 78 divided by 2. This should be 39. Hold on, I'm right. 77 divided by 2, that's 38.5. This is 67 divided by 2. This will be 33.5. Forgive me, I'm having a senior moment. So this is 33.5 for 33 and 34. 33 plus 33 is 66 divided by 2, which is 33. 33 and 14 is 47 divided by 2, which is 23.5. 14 plus 44 is going to be 58 divided by 2, which is 29. 14 plus 34, that's 48 divided by 2, which will be 24. 14 plus 33 is 47 divided by 2, which is 23.5. And finally, 14 plus 14, which is 28 divided by 2, which is 14. Okay, so these are all the means for each one of these sample means, and that's a long list here. But we're going to shorten this list into a probability distribution here. So here we got X bar, which is our sample mean of 2, and the probability. And in this case here, the numbers that I have here are 14, and then 23.5. I'm putting all these in numerical order. And then 24, 29, 33, 33.5, 34, 38.5, 39, and 44. And I want their probabilities here. So for 14, there's only one number that gave me a mean of 14, and that's 14 and 14, which gave me a mean of 14. And that's only 1 out of 16. So for 14, this probability is 1 out of 16. Now for 23.5, there are 2 numbers. They gave me a mean of 23.5. 2 numbers, they gave me a mean of 23.5. And those are the 2 right here. And that's out of 16. So we're going to leave this as, for 23.5, 2 over 16. And then for 24, from this list, there is only 1 and 2. Okay, because for 34 and 14, they gave me an average of 24. 14 and 34 also gave me an average of 24. So there's 2 numbers with a mean of 24 out of 16. Or 2 samples, they gave me a mean of 24 out of 16. 29, also there's 2. That 44 and 14, and the 44 and 14. Again, 2 out of 16. And then for 33, there's only 1 number that gave me an average of 33 out of 16, or 1 sample mean. 33.5, in this case, there are actually 2 out of 16. Here's 1, and here's the other. So in this case, that's 2 out of 16. And then for 34, I only see 1 out of 16. And then for 38.5, I see 1, 2 out of 16. For 39, there's 1. There's 1, and there's 2 out of 16. And for 44, there's only 1. They gave me a mean of 44 out of 16. Okay, so that's your probability distribution here. I know this is very difficult to fit all of this in this small space that I have. But that's your probability distribution here. Okay, now part B is to find the mean of the sampling distributions here. Okay. And that's your mu right here. And that's going to be equal to 14 times 1 over 16. What I'm doing here is taking each individual sample mean and multiplying it by its respective probability. So it'll be 1 times 14 over 16 plus 23.5 times 2 over 16 plus 24 times 2 over 16 plus 29 times 2 over 16 plus 33 times 1 over 16 plus 33.5 times 2 over 16 plus 34 times 1 over 16 plus 38.5 times 2 over 16. This is all coming from that probability distribution table, plus 39 times 2 over 16 plus 44 times 1 over 16. Okay. Now, if you take the time and type all of this in your calculator, your mean should be 31.25. Okay. Now, the other part, if you were to compare that with the mean of your population, that's your mu, you just take these numbers, so 44 and 34, 33 and 14, add those numbers together and divide by 4. that sum is 125, and then you divide that by 4, you'll get 31.25. You can see that the mean of the population is the same as the mean of all your sample. Okay? So here the sample mean is equal to the mean of the entire population, meaning that the means will always be equal because the mean is considered to be an unbiased estimator, because the sample mean will always target the population mean. Okay, we already talked about that earlier. It's one of your 3 unbiased estimators. Okay. All right, let's look at the next example. The ages in years of 3 government officials when they died in office were 54, 45, and 61. Complete parts A through D. Part A is this. Assuming that 2 of the ages are randomly selected with replacement, lists the different possible samples. Okay, so in this case here, we only got 3, so we know we're going to have 9 different possible samples here. So if we start off with 54, we can choose itself. The next one will be 54. We can choose 45. The next one will be 54, and we can choose 61. And then next, if we choose 45, we start with 45, then 45 can be paired with 54, and then 45 can be paired with itself, and also 45 can be paired with 61. And finally, if we use 61, then that can be paired with 54, and then 61 can be paired with 45, and finally 61 can be paired with itself. Okay, so these are all the possible samples if we're choosing 2 of the ages randomly selected with replacement. And then part B, find the range of the samples and then summarize the sampling distribution of the ranges in the format of a table representing the probability distribution. Okay, in this case here, we have a sample of n is equal to 2, and we're finding the range. The range is always the largest number minus the smallest number. Okay, so I'm going to list all the samples, possible samples of n is equal to 2. So we got 54 and 54, then 54 and 45, then 54, 61, and then 45 and 54, and then 45 and 45, then 45, 61, 61, 54, 61, 45, 61, 61. Okay, in this case here, the range is the largest number minus the smallest number. So if we do 54 minus 54, that's 0. For this next one, 54 minus 45 will be 9. And then 54 minus 61, or 61 minus 54, is going to give you 7. Largest minus the smallest. And then for this one, 54 minus 45, that would be 9. Then 45 minus 45 is 0. Let's say 61 minus 45, that's going to give us 16. And then 61 minus 54 would give us 7. 61 minus 45, that would give us 16. And finally, 61 minus 61 is 0. So the only numbers that I see here are the 0, 7, 9, and 16. So here, on the right side, sample range, and probability. So again, I see 7, 0, 7, 9, and 16. I'm going to list their probabilities individually. For 0, there are 3 numbers with 0 out of 9. So that probability for 0 in our sample range is 3/9. For 7, only 2, so that's 2/9. For 9, there's 1, 2 out of 9. So that's also 2/9. 16, there's also 2 out of 9. So that's going to be 2/9 as well. So this is going to be, part B is that probability distribution in the form of a table. Now part C, compare the population range to the mean of the sample ranges. Okay, so now with our numbers 54, 45, and 61, the range, that's this set of data, that's the population here. The range of that population, the largest minus the smallest, that's 61 minus 45, and that will give you 16. So that's the range of the entire population here. Now for the mean of the sample range, I'm calling this mu of the sample range. We can take that table and add these individual numbers together in this column and divide by 9. Okay, so in this case here, we can add 0 plus 9 plus 7 plus 9 plus 0 plus 16 plus 7 plus 16 plus 0. And that sum is going to be divided by 9. And by looking at this, that's going to give me 25, 41, 48, 64. And 64 divided by 9 is going to give me 7.1 repeating, which is not the same as the range of that entire population. So in this case here, when we answer part D, do the sample ranges target the value of the population range? Okay, so in general, do the sample ranges make a good estimate of the population ranges? In this case, the answer there will be no. So here the sample ranges do not target the population range because they're not the same. And as a result, those sample ranges do not make good estimates of the population range. Okay. Okay. Last example for this video. And that's this. A genetics experiment involves a population of fruit flies containing 2 males named Billy and Christopher and 2 females named Dana and Aaron. Assume that 2 fruit flies are randomly selected with replacement. And in part 8, after listing the possible samples and finding the proportion of females in each sample, use a table to describe the sampling distribution of the proportion of females. So in this case here, I'm going to use letters here. I'm going to let B represent Billy, C represent Christopher, D represent Dana, E represent Aaron. Okay. Now this one's going to have 16 because they're 4. Okay. Now, let me go ahead and show you how this is done. Okay. Here you have a sample of n is equal to 2. So here, with Billy, we can choose itself on the second time with replacement. And then B and C will be Billy and Christopher. And then next is Billy and Dana. And then next is Billy and Aaron. Okay. And then Christopher and Billy. Then Christopher and himself. Christopher and Dana. Christopher and Aaron. And then for Dana being chose first, we can have Dana and then Billy. Dana, then Christopher. Then Dana and herself again. Dana and Aaron. And then finally, Aaron and Billy, then Aaron and Christopher, Aaron and Dana, and then Aaron and herself. Now we want the proportion of females from a sample of 2. Now, Billy and Christopher are males, Dana and Aaron are females. So for Billy and Billy, the proportion of females is 0. For Billy and Christopher, that proportion is also 0. For Billy and Dana, that proportion is 0.5 because Dana is a female. Billy and Aaron, Aaron is a female, so that proportion is 0.5. That's 1 out of 2. Okay, now for Christopher and Billy, that proportion of females is 0. Christopher and himself, that proportion is also 0. Christopher and Dana, Dana is a female, so 0.5. That represents a proportion of females. Christopher and Aaron, that's 1 female out of 2, so that's 0.5 for his proportion. Now, Dana and Billy. Here, there's 1 female, so that's 1 out of 2 or 0.5. Dana and Christopher, that's 1 female again, that's also 0.5. Dana and herself, that's a female twice. 2 out of 2, which is going to be 1. Dana and Aaron, they're both females, so that's 2 out of 2, which will be 1. And then for Aaron, Aaron will be paired with Billy. That's 1 female, or 0.5. Aaron and Christopher, that's 1 female, that's also 0.5. Aaron and Dana, they're both females, so that's 2 out of 2, which is 1. And then Aaron and Aaron, that's 2 out of 2 again, that's going to be equal to 1. Now we're going to condense that into a probability distribution with the proportion of females here. The only numbers there for proportion are 0, 0.5, and 1. Now if you count up the number of zeros in our proportion, there are 1, 2, 3, 4 out of 16. So that probability for 0 is 4/16. For 0.5, there's 8. We see 1, 2, 3, 4, 5, 6, 7, 8 out of 16. And then for 1, there's 4. As you can see, 1, 2, 3, 4 out of 16. So that probability will be 4/16. Okay, so this represents your probability distribution. Now we want to find the mean of the sampling distribution. Okay, well that mean is this. We take 0 and multiply that by 4/16. We take 0.5 and multiply that by 8/16. And then we take 1 and multiply that by 4/16. Now if you take the time and put all this in the calculator, you'll see that your population mean for this will be 0.5. So the mean of the sampling distribution will be 0.5. And then part C is the mean of the sampling distribution from part B equal to the proportion of females. If so, does the mean of the sampling distribution of proportions always equal the population proportion? Well, there are 2 females out of 4 fruit flies. So 2 out of 4 would give you 0.5. And in this case, your sample mean is equal to the population proportion of females. So that means that those values are always equal because the proportion is an unbiased estimator. That's one of our 3 unbiased estimators, if you recall. Okay. Okay, so this will conclude this particular video on sampling distributions and estimators.